In this example, we're going to take really everything that we've talked about in this section so far and try and put it all together in one single problem. So problems like these are really, really good practice because it forces you to practice everything that we've talked about in this section. So we are going to work with the function f of x equals x cubed minus 9x squared plus 24x minus 10. We are going to find the intervals where f of x is increasing, where f of x is decreasing. We're going to find the local extrema, and then at the end of this problem, we're actually going to go ahead and construct a graph of f of x. Now, these sketches, they don't need to be super detailed. There's usually only a couple points. The points that I really care about are the local extrema. I won't even label the other points or the other y values. It's just those local extrema that we really, really care about. So we'll talk about that when we get there. So if I want to determine where this function is increasing and where it's decreasing, if I'm thinking about local extrema, I'm thinking about the first derivative. So I'm thinking about f prime of x. So f prime of x for this problem, I can just use my power rule to give me 3x squared minus 18x plus 24. And I want to think about critical numbers, which actually, oops, I skipped a step here. For critical numbers, remember, we want to think about what is the domain of this function here. What is the domain of our original function? And in this case, we're working with a polynomial. So the domain will be negative infinity to positive infinity. So we're not going to have any issues there. We're not going to have any holes or asymptotes or anything weird like that. So we have our first derivative. We want to think about places where f prime is equal to 0 and places where f prime does not exist. So I'll start by taking 3x squared minus 18x plus 24, setting it equal to 0 and solving for x. Now we can factor this, we can use the quadratic formula, we could complete the square. No matter what you do, I would factor out 3 on that left-hand side since all of those share a common factor of 3. And that'll leave me with x squared minus 6x plus 8 is equal to 0. And now I can factor that a little bit easier. Two numbers which multiply to be a positive 8, add to be a negative 6. That would be negative 2 and negative 4. So x minus 2 times x minus 4 equals 0. And then I can take each factor, x minus 2 equals 0, and set it equal to 0. So we'll end up with an x equals positive 2, and x minus 4 equals 0 gives me x equals positive 4. So here are two critical numbers that I have. I've got positive 2 and positive 4. But remember, we also want to think about the places where f prime does not exist. It's just a good habit to kind of always be thinking about that. And in this case, f prime, if I look at the equation of f prime, it's a polynomial. So f prime is a polynomial, which means it exists everywhere, which means we don't have any other critical numbers. It's just the two that we've already found. So that's good. We only have two critical numbers. We've got x equals 2 and we've got x equals 4. So at this point, kind of doesn't really matter whether we're thinking about where it's increasing or where it's decreasing or the local extrema. All three of those things, I'm going to want to build a sign chart for my derivative. So I'm going to do that just a little bit below here. And I'm going to label it as f prime. Here we've got x equals 2. We've got x equals 4. And I want to include the behavior of these two critical numbers. What was the derivative doing at those two critical numbers? Because that's going to have a really big impact on the graph of this function. Well, we found those two by taking the derivative and setting it equal to 0. So right above those two, I'm just going to put a little 0 right above there to show that the derivative was equal to 0 at that point. And as I'm thinking ahead to graphing this function in the last part of this problem, that derivative being 0 is really important. What that tells me that at x equals 2 and at x equals 4, I have a horizontal tangent line. So I'm just going to make a note to myself that at those two particular x values, we have horizontal tangent lines. So now I need to figure out where is this function increasing and where is this function decreasing. So we're going to take some numbers and plug those into our first derivative. So real quick, just to copy and paste our first derivative down there so that we've got it in front of us. All right, here's our first derivative. So first I need a number on the left-hand side of x equals 2. So I'm going to work with 0 just because it makes our work a little bit easier. F prime of 0 is going to be 3 times 0 squared minus 18 times 0 plus 24. This should give me 0 minus 0 plus 24 would be a positive 24 here. So f prime, my derivative is positive, it's increasing. I've got the sign for that part. Next, I need a number between 2 and 4. So x equals 3 is probably the easiest choice. If you really wanted to, you could pick a decimal or a fraction or something like that, but I think 3 is going to make for the easiest computations here. So we'll have 3 times 3 squared minus 18 times 3 plus 24. Oops. And then if I take that and plug that into my function, I should end up with negative 3 for my derivative. So that means that the first derivative is negative in between 2 and 4. And then finally, we'll take a number on the right-hand side of 4. So we could pick 5, 6, 7, 8, 9, 10. I'm going to pick 5. So f prime of 5 is equal to 3 times 5 squared minus 18 times 5 plus 24. And this time around, when I take 5 and plug that in, I ended up with a positive 9. So my first derivative is positive on the right-hand side of 4. So I can already say a few things about this function. I can already kind of give part of my answer right now. I can say, well, this graph is increasing on negative infinity to positive 2, so that's this interval right here, and then positive 4 to positive infinity, so that interval and 4 to positive infinity. It is decreasing in the middle, so that would be on the interval 2 to 4. So there's part of my solution already. We've got that. My next step then, I want to think about, do I have any local extrema? And in this case, we're looking for sign changes in our first derivative. So first of all, at x equals 2, it changes from positive to negative. And if you have a hard time imagining what that looks like, draw that in. If f prime is positive, that means my function is increasing. And if f prime is negative, it's decreasing. So it's increasing and it's decreasing. So that means I have a local maximum at x equals 2. We'll go and find the y value in just a moment. And then on the right-hand side of 4 over here, it switches to positive once again, so that means it's increasing. So that means I'm going to have a local minimum at x equals 4. So we know that we have these local extrema. The last thing that I need to do then, in order to give my answer, is to actually go and find the y values corresponding to those. And remember, for the y values, we want to look all the way back at what was our original function. What did we start with? So we started with x cubed minus 9x squared plus 24x minus 10. So I'm going to write that down here just so that I don't forget it. F of x equals, let's see, x cubed minus 9x squared plus 24x minus 10. And we'll take x equals 2 and x equals 4 and plug those in so that we can find our y values. So f of 2 is going to be 2 to the third minus 9 times 2 squared plus 24 times 2 minus 10. And we can go ahead and crunch some numbers there, but I end up with a positive 10 there. So we said at 2 we had a maximum, so I'm just going to make a note to myself that we have a local max at 2 comma 10. And then for our minimum at 4, we got to plug that in as well. So f of 4, this is 4 to the third minus 9 times 4 squared plus 24 times 4 minus 10. So if I take positive 4, plug that in, I ended up with positive 6. So I have a local minimum at, what did I say, 4 comma 6. So here is a big chunk of my answer already. I figured out where is my function increasing. I've said here's where it's decreasing, and then here are the local extrema. So this is just like what we've kind of been doing up until this point. We've used the first derivative test to really answer most of this question for us. The last thing that we want to do then is we want to sketch a graph of our function using what we found. I want to take what we found and make a rough sketch of it. So when I start these problems, when I start with curve sketching, the things I want to start with first, the things I think that are easiest to start with, I'm going to start with any local extrema that I have. So I'm going to start by plotting the point 2 comma 10 and 4 comma 6. So let's see. I'm mostly concerned with that first quadrant. 1, 2, 3, 4. And we'll do, let's just I'm going to leave my my y-axis by 2. So 2, 4, 6, 8, 10. So we said that we have a point at 2 comma 10 and then at 4 comma 6. So that would put me right here. So, and usually what I like to do as I'm sketching the graphs of these is I like to make a note to myself. Why are these points important? What's going on there? So at 2 comma 10, we said, well, that was a maximum. And at 4 comma 6, here we had a minimum. The other thing that I want to know is I want to know, do I have any horizontal tangent lines at these 2 points that I've just plotted? And what I'm looking for that is I'm looking for what was the value of the derivative at those points. Now we said they were both 0 at those points, which is what we're looking for, and we already told ourselves that we're going to have a horizontal tangent line at those 2 points. So I'm just going to include, a horizontal tangent line there. It's not necessarily a part of our graph, but it does help us be more precise with the actual curve sketching part of it. And as far as the behavior of it, we know we're going to have a horizontal tangent line. It's easier to see when we draw that in. After that, I like to look at this and I say, okay, let's start with here. Let's start with this maximum. I know if it's a maximum with a horizontal tangent line, it's going to be increasing on the left-hand side. It's going to be decreasing on the right-hand side. And then once I get to this minimum right here, we're going to have the opposite effect where it's going to be decreasing. It needs to kind of level out so that we hit that horizontal tangent line and then switch to increasing after that. So it should look something like this. For the ends, you're just going to continue the trends that you already see. So it's on the left-hand side here, it's going to be increasing, and on the right-hand side, it should also be increasing. So this is about the level of sketch that I think you should be able to do. You should be able to include your local extreme values, any horizontal tangent lines in, and then I should just be able to see the overall behavior of the graph. I want to know, where is this function increasing and where is this function decreasing, which should actually already be built in if you've included your minimum and maximum values. So take your time with these problems. They're really, really, really good practice. I think it's the best thing that you can do to practice the types of problems that we're going to be looking at in this section.